So hello everyone, in this audio class we will read the chapter number 4 map projections from the book Practical Work in Geography class 11 NCERT Practical Book part 1. So let's get started with the chapter 4 map projections. What is map projection? Why are map projections drawn? What are the different types of projections? Which projection is most suitably used for which area? In this chapter, we will seek the answers of such essential questions. First point is map projections. So, map projection is the method of transferring the graticules of latitude and longitude on a plane surface. It can also be defined as the transformation of spherical network of parallels and meridians on a plane surface. As you know that the earth on which we live is not flat. It is geoid in shape like a sphere. A globe is the best model of the earth. Due to this property of the globe, the shape and sizes of continents and oceans are accurately shown on it. It also shows the directions and distances very accurately. The globe is divided into various segments by the lines of latitude and longitude. The horizontal lines represent the parallels of latitude and the vertical lines represent the meridians of the longitude. The network of parallels and the meridians is called graticule. The network facilitates drawing of maps. Drawing of the graticule on a flat surface is called projection. But a globe has many limitations. It is expensive. It can neither be carried everywhere easily nor can a minor detail be shown on it. Besides, on the globe the meridians are semicircles and the parallels are circles. When they are transferred on a plane surface, they become intersecting straight lines or curved lines. Next point is need for map projection. The need for a map projection mainly arises to have a detailed study of a region, which is not possible to from a globe. Similarly, it is not easy to compare two natural regions on a globe. Therefore, drawing accurate large-scale maps on a flat paper is required. Now the problem is how to transfer these lines of latitudes and longitudes on a flat sheet. If we stick a flat paper over the globe, it will not coincide with it over a large surface without being distorted. If we throw light from the center of the globe, we get a distorted picture of the globe in those parts of paper away from the line or points over which it touches the globe. The distortion increases with increase in distance from the tangential point. So tracing all the properties like shape, size and directions from a globe is nearly impossible because the globe is not a developable surface. In map projection, we try to represent a good model of any part of the earth in its true shape and dimension, but distortion in some form or other is inevitable. To avoid this distortion, various methods have been devised and many types of projections are drawn. Due to this reason, map projection is also defined as a study of different methods which have been tried to transferring the lines of graticules from the globe to a flat sheet of paper. Next point is map projection. So map projection is the system of transformation of a spherical surface onto a plane surface. It is carried out by an orderly and systematic representation of the parallels of latitude and meridians of longitude of the spherical earth and part of it on a plane surface on a conveniently chosen scale. Next point is lexodrome or rhomb line. So it is a straight line drawn on Mercator's projection joining any two points having a constant bearing. It is very useful in determining the directions during navigation. The next point is great circle. So great circle, it represents the shortest route between 2 points, which is often used both in air and ocean navigation. Next point is homolographic projection. So a projection in which the network of latitudes and longitudes is developed in such a way that every graticule on the map is equal in area to the corresponding graticule on the globe. It is known as the equal area projection. Next is orthomorphic projection. So the projection in which the correct shape of a given area of the surface is preserved. Next point is elements of map projection. So first is elements of map projection. First element is reduced earth. A model of the earth is represented by the help of a reduced scale on a flat sheet of paper. This model is called the reduced earth. The model should be more or less spheroid, having the length of polar diameter lesser than the equatorial, and on this model the network of graticule can be transferred. Next point is next element is parallels of latitude. So these are the circles running around the globe parallel to the equator and maintaining uniform distance from the poles. Each parallel lies wholly in its plane, which is right angle to the axis of the earth. They are not of equal length. They range from a point at each pole to the circumference of the globe at the equator. They are demarcated as 0 degree to 90 degree north and south latitudes. Next element is meridians of longitude. These are semicircles drawn in north-south direction from one pole to other, and the two opposite meridians make a complete circle, that is circumference of the globe. Each meridian lies wholly in its plane, but all intersect at right angle along the axis of the globe. There is no obvious central meridian, but for convenience an arbitrary choice is made, namely the meridian of Greenwich, which is demarcated as 0 degree longitudes. It is used as a reference longitudes to draw all other longitudes. Next point is global property. In preparing a map projection, the following basic properties of the globe surface are to be preserved by using one or the other methods. First is distance between any given points of a region, then shape of the region, then size or area of the region in accuracy, then direction of any one point of the region bearing to another point. Next is classification of map projection. So map projections may be classified on following basis. First is drawing techniques. On the basis of the method of construction, projections are generally classified into perspective and non-perspective and conventional or mathematical. Perspective projections can be drawn taking the help of source of light by projecting the image of a network, parallels and meridians of a globe on a developable surface. Non-perspective projections are developed without the help of source of light or casting shadow on surfaces, which can be flattened. Mathematical or conventional projections are those which are derived by mathematical computation and formula and have little relations with the projected image. Next point is developable surface. A developable surface is one which can be flattened and on which a network of latitude and longitude can be projected. A non-developable surface is one which cannot be flattened without shrinking, breaking or creasing. A globe or spherical surface has the property of non-developable surface, whereas a cylinder, a cone and a plane have the property of developable surface. On the basis of nature of developable surface, the projections are classified as cylindrical, conical and zenithal projections. Cylindrical projections are made through the use of cylindrical developable surface. A paper-made cylinder covers the globe and the parallels and meridians are projected on it. When the cylinder is cut open, it provides a cylindrical projections on the plane sheet. A conical projection is drawn by wrapping a cone round the globe and the shadow of graticule network is projected on it. When the cone is cut open, a projection is obtained on a flat sheet. Zenithal projection is directly obtained on a plane surface when a plane touches the globe at a point and the graticules are projected on it. Generally, the plane is so placed on the globe that it touches the globe at one of the poles. These projections are further subdivided into normal, oblique or polar as the position of the plane touching the globe. If the developable surface touches the globe at the equator, it is called the equatorial or normal projection. If it is tangential to a point between the pole and equator, it is called the oblique projection, and if it is tangential to the pole, it is called the polar projection. Next point is global properties. As mentioned above, the correctness of the area, shape, direction and distances are the four major global properties to be preserved in a map. But none of the projections can maintain all these properties simultaneously. Therefore, according to a specific need, a projection can be drawn so that the desired quality may be retained. Thus, on the basis of global properties, projections are classified into equal area, orthomorphic, azimuthal and equidistant projections. Equal area projection is also called the homolographic projection. It is that projection in which the areas of various parts of the earth is represented correctly. Orthomorphic or true shape projection is one in which shapes of various areas are portrayed correctly. The shape is generally maintained at the cost of correctness of the area. Azimuthal or true bearing projection is one on which direction of all points from the center is correctly represented. Equidistance or true scale projection is that where the distance or scale is correctly maintained. However, there is no such projection which maintains the scales correctly throughout. It can be maintained correctly along some selected parallels and meridians as per the requirement. Next point is source of light. So on the basis of location of source of light, projections may be classified as mnemonic, stereographic and orthographic. Mnemonic projection is obtained by putting the light at the center of the globe. Stereographic projection is drawn when the source of light is placed at the periphery of the globe, at a point diametrically opposite to the point at which the plane surface touches the globe. Orthographic projection is drawn in when the source of light is placed at infinity from the globe, opposite to the point at which the plane surface touches the globe. Next point is constructing some selected projection. First is conical projection with one standard parallel. So a conical projection is one which is drawn by projecting the image of graticules of a globe on a developable cone, which touches the globe along the parallel of latitude called the standard parallel. As the cone touches the globe located along AB, the position of this parallel on the globe coinciding with that of the cone is taken as the standard parallel. The length of other parallels on either side of the parallel are distorted. So next is properties of conical projection. So all the parallels are arcs of concentric circles and equally spaced. All meridians are straight lines merging at the poles. The meridians intersect the parallels at right angles. The scale, number 3, properties of conical projection. The scale along all the meridians is true. That is, the distances along the meridians are accurate. The arc of a circle represents the pole. The arc of a circle represents the pole. The scale is true along the standard parallel but exaggerated away from the standard parallel. Meridians become closer to each other towards the pole. This projection is neither equal area nor orthomorphic. So limitations of conical projection. So it is not suitable for world map due to extreme distortions in hemisphere opposite to one in which the standard parallel is selected. Even within the hemisphere, it is not suitable for representing larger areas as the distortion along the pole and near the equator is larger. Next point is uses. This projection is commonly used for showing areas of mid-latitudes with limited latitudinal and larger longitudinal extent. A long narrow strip of land running parallel to the standard parallel and having east-west stretch is correctly shown on this projection. Direction along standard parallel is used to show railways, roads, narrow river valleys and international boundaries. This projection is suitable for showing the Canadian Pacific Railways, Trans-Siberian Railways, international boundaries between USA and Canada and the Narmada Valley. Next is cylindrical equal area projection. So the cylindrical equal area projection, also known as the Lambert projection, has been derived by projecting the surface of the globe with parallel rays on a cylinder touching it at the equator. Both the parallels and meridians are projected as straight lines intersecting one another at right angles. The pole is shown with a parallel equal to the equator, hence the shape of the area gets highly distorted at the higher latitude. Next is properties of cylindrical equal area projection. So all parallels and meridians are straight lines intersecting each other at right angles. Polar parallel is also equal to the equator. So scale is true only along the equator. What are the limitations of cylindrical equal area projection? So distortion increases as we move towards the pole. The projection is non-orthomorphic. Equality of area is maintained at the cost of distortion in shape. Next is uses of cylindrical equal area projections. So the projection is most suitable for the area lying between 45° north and south latitudes. It is suitable to show the distribution of tropical crops like rice, tea, coffee, rubber and sugarcane. Next point is Mercator's projection. So a Dutch cartographer Mercator Gerardus Karmait developed this projection in 1569. The projection is based on mathematical formula. So it is an orthomorphic projection in which the correct shape is maintained. The distance between the parallels increases towards the pole. Like cylindrical projection, the parallels and meridians intersect at a right angle. It has the characteristics of showing correct directions, as a straight line joining any 2 points on the projection gives a constant bearing, which is called the loxodrome or rhomb line. So properties of Mercator's projection: all parallels and meridians are straight lines and they intersect at each other at the right angles. All parallels have the same length, which is equal to the length of equator. Or meridians have the same length and equal spacing, but they are longer than the corresponding meridian on the globe. Spacing between the parallels increases towards the pole. Scale along the equator is correct as it is the equal of length of the equator on the globe, but the other parallels are longer than the corresponding parallel on the globe. Hence, the scale is not correct along them. For example, the 30° parallel is 1.154 times longer than the corresponding parallel on the globe. So shape of the area is maintained, but the higher latitudes distortion takes place. The shape of small countries. The shape of the small countries near the equator is truly preserved while it increases towards the poles. It is azimuthal projection. It is the orthomorphic projection as the scale along the meridian is equal to it is an orthomorphic projection as a scale along the meridian equal to the scale along the parallels. So what are the limitations of Mercator's projection? So there is a great exaggeration of scale along the parallels and meridians in high latitudes. As a result, size of the countries near The pole is highly exaggerated. For example, the size of Greenland equals to the size of USA, whereas it is only 1/10 of USA. Poles in this projection cannot be shown at 90-degree parallel, and meridians stretching them are infinite. What are the uses of Mercator's projection? So more suitable for world map, are widely used in preparing atlas maps, very useful for navigation purposes, showing sea routes and air routes, drainage pattern, ocean currents, temperature, winds and their direction, distribution of worldwide rainfall and other weather elements are appropriately shown on this map. So this is for today. Thanks for listening. Keep listening for further audio classes. Thank you.